So I was looking around for a decent quality headphone amplifier, and this would go from a stereo line level signal to conventional headphones using a 1/4 inch stereo headphone jack. There's quite a few amps out there that are made for small, lightweight headphones that are not much more than glorified earbuds with a strap over the top of your head, but I'm talking about conventional, full-powered, 8 ohm or whatever stereo headphones, almost, professional quality ones. And a lot of the designs I looked for online just didn't look like they were going to cut it, and this one seemed to get a couple of good reviews on various places online. What I saw, the schematic made it look like a design I would approve of, or maybe even consider doing myself. And there's several places offering kits of it. This is on eBay. It's the HA-PRO2, and that's what this is called. It's that design. And so a kit was $11.88 with the circuit board and all the parts except for like the case and the power transformer and a couple other sundry items, and it's coming out of China. A $3.88 speed pack from China, Hong Kong, Taiwan, whatever. This actually came very quickly. It was less than 2 weeks after I ordered it. And it didn't come directly from China. It went to some clearinghouse in, where was it, like in Georgia or somewhere, that repackaged it apparently, because the box coming from there didn't indicate anything about coming from China, but all the tracking information said it was coming from China. So I think that's the way some of these guys do it. They have arrangements with some sort of a forwarding center in the States that then, maybe undoes a bulk packaging and individually packages it for domestic shipment. And then I also got, on eBay, this matching full aluminum case that fits the HA-PRO series headphones. It was $18, although the shipping was even more than the kit itself, or the case itself, but I didn't see any better deals, except for one place that promised about a 3-month long delivery time, so I didn't want to wait for that. So I coughed up the extra money. And this also came, it took about an extra week and a half after the amplifier arrived, but still not too bad for a shipment coming from China. And since I was going through eBay and not through one of the, Ali or whatever it is, that I would consider be somewhat less reputable online stores, I felt better buying it through eBay. Once again, this came in and it was forwarded through somewhere in the American Southeast. Obviously repackaged. The box I got didn't say anything about China on it. But once again, the tracking said, charted its whole shipment from China over here. So those are the two basic parts. I'm still going to have to buy a few things, but I need to do a preliminary exploration of exactly what I've got and what I still need to get. Alright, here's the contents of the package with the case. Looks like two pretty good quality black anodized aluminum shells and a big heavy aluminum plate that's black anodized and milled, and an even heavier plate which is clear anodized and milled, and a snap-in IEC power connector, a SPDT 2-position toggle switch, clearly for the power, and a big aluminum knob with a nylon or something insert, and 6 of 2 different sizes of bolts. I'm pretty sure that the stainless steel looking bolts will be the ones that go from the front here, and the flathead black anodized ones will go here. I don't know if the other two of each ones are spares or if they get used somehow else in this, but those are the basic parts there. And here's the kit. Let me open that bag up. So here are all the components in the parts bag. You've got the double-sided circuit board, obviously a high quality board, fiberglass construction, double-sided silk screened. All the parts are designated by their part numbers or values. There does have LJM_LJM@foxmail.com. So the assembly is kind of straightforward even without any documentation, just because you match up the values. There are no sockets provided for the ICs. I'll probably put those in. But the parts all look like they're reasonable quality. There's, interestingly enough, one diode already stuck on the board but not soldered. And this is, by the way, all through hole. There's no surface mount on this. So we have a couple of what are probably voltage regulators. I don't know, 7812. There's probably a 7912, but I can't see it easily. Full wave diode bridge. I don't know if these are transistors or what they are. Have to get the magnifying glass out to read what they are. The amplifiers, I think, are just op amps. Once again, I can't make them out, but on the circuit board it calls them 48 or 4580s. They're all the same. And some electrolytics and other types of capacitors. There's a terminal block that I think is for the incoming power from the power transformer. And there's this type of a jack. I think this is one of the headphone jacks, and I think this is the other headphone jack for the 1/4 inch size. Looks like a pretty robust jack. Doesn't look like a cheap one. And a dual 50K volume control potentiometer. And a small relay. So obviously the power connector is going to be back here. Power supply section, I can see the regulators, filter capacitors. I believe, yeah, this is the inputs here. So it'll be, you know, a ground and 2 signals for left and right. And I don't see that they've provided the jacks for this, so I guess you're kind of on your own in that regard, whatever type of jack you want to use. Not sure what the relay does yet. There's the place for the big headphone jack and the small headphone jack, and then the potentiometer. So I want to see how all this stuff fits into the case. So here's the basic layout. The main headphone jack and the pot do line up at the proper heights and spacings, and they do fit the board when the board slides into the channel on the base shell. The power connector does snap into the rear panel properly. Not sure what that cutout is. It could be that, I don't know, have no idea what would have that shape actually. This knob obviously will go onto here alright and fit into that recess. I have no doubt that the power switch will fit that, and the green LED that's provided will poke through that hole, and it lines up with the hole on the circuit board. So that all looks good. The input terminals here are in line with these holes in the back. The trick will be to find connectors that go with that spacing. I expect I'll use RCA type jacks for that. And then I need to find a transformer that'll sit over here in the corner and provide, I believe it needs a 24 volt center tapped transformer. There's no, yeah, it does say a 12-0-12, so a center tapped 12 on either side or 24 volt center tapped transformer. Be nice if it had a fuse in it, so I could mount a fuse holder in here and a transformer. I have to look and see what size of transformer I can get that goes on here. Will fit into this space. Probably nothing should go here, and I'd like to have these leads be as far from the power transformer as possible. All the low-end audio stuff is all over here, so distance is good. Keep the transformer over here. So I have to take measurements and see what'll fit and make a purchase. Yeah, and then find what kind of RCA jacks will fit. Those may be the only things I need to order. Alright, so in this hodgepodge of a project, I've got to do a little case modification. This is the case that's ostensibly for this kit. And one of the first problems is I'm thinking that it's going to be best to have the circuit ground isolated from the case ground. Or at least have the option of having it isolated. The circuit board is obviously not designed to go in this case. It's designed to have 4 spacers supporting it from a case. This case is a generic design that has slots to slip in a circuit board, but the board is not really laid out for that. It has foil areas coming under the slot, which is never good. Now everywhere where it does that, that's the ground plane, and this is the only place that isn't covered with solder mask that might make contact. And then there's the anodizing, which isn't a very good conductor either, but it's going to be really difficult to modify this product to not have any grounds come in contact with the case. I could probably chew away with a grinder at the foils along the edges, but then you've got areas like this. It could be done, but it'd be messy. So I think what I'm going to do initially is put it in here and see if the solder mask does the trick. That if it's an adequate insulator, I may not have to do anything else. There's certainly not room to add an insulator. The spacing is quite tight there. There's very little gap. Certainly nothing I would have in the way of a thin insulating film could be slipped in there. But this one place where there's a ground pad is certainly an unsolder masked area that has the best chance of contacting it. So first I'm going to mill out just a little bit of the rail, top and bottom there, so it does not make contact with this pad here. Then I'm going to do a continuity test and see if there's any other need to do anything in this area. Here are the RCA jacks that I selected. They are a type that's designed to be insulated from the case they're mounted on and come with all the hardware necessary for that. And their insulating inserts fit the holes in the back panel of the case perfectly. I selected the Telema brand 62052 toroid transformer, which provides dual 115 volt primary windings, so it can be used for 115 volt or 230 volt line voltages, and it has dual 12 volt secondaries, so it can be wired up as if it were a 24 volt center tapped secondary. The only downside is that it's really about 3 times the necessary VA rating, and that's not a bad thing. It just makes it a little larger and heavier than it really needs to be. And the part number from DigiKey is listed here on the label. The transformer is a 15 VA, which is equivalent to a roughly 600 milliamp secondary current. That's maximum. And if you work the 15 VA into a typical 115 volt line level, you end up with a pretty small value of fuse that you would use if you're going to fuse this. Somewhere in the ballpark of 1/10 of an amp on the primary, which is what I ended up fusing this for. And I decided to use a 3 AG size glass fuse, which is a real typical size, and in a slow blow because it's running the inductive load, so you don't want it to be a fast blow that'll pop every time you turn the power switch on. And I got this Keystone brand 3 AG fuse holder. Here's the DigiKey part number for that. If worst came to worst, I could mill out the rails entirely in this area, not use these rails to support the board, and then drill through and put screws through into the case. But I'd really prefer not to go there. The second thing is that the circuit board I have is different than the version that this case is designed for. The circuit board has provision for both a 1/4 inch and an 1/8 inch headphone jack, which I plan to have, but there's no hole machined in the front panel for the 1/8 inch jack, so I'm going to have to add that. And then finally, I have to, well, not finally, I have to make a hole for my fuse holder and for my toroid transformer. And finally, I need to put something here. I don't know what this hole was there for originally. Possibly for a USB power source or something, but this being a bipolar supply, a USB supply would be the greatest thing to have. I plan to put a little panel on here and mount this extra switch to it, just sticking through that square hole. And this will be the thing that does the deliberate bonding of the circuit ground to the case. Now the case will be tied to earth ground through the power cord. So I expect to have the earth terminal on the power cord here go to a grounding lug located somewhere in this area, and then I'm going to have the ground connectors of the 2 RCA plugs wired to circuit ground, and then also through the switch here to the ground terminal. So this will be my bonding switch. So I need to make holes for all of those things and do a little bit of milling. Well, I went in a little bit too far in there and scraped a little of the anodization off the edge there, but it's definitely a nice high clearance area where I won't have any trouble with that particular point contacting the case. So now I have to temporarily put the back on and make sure I know exactly where to mount my transformer. So I've made a little aluminum bracket to hold the bonding switch and centered it in the hole, and drilled a couple of pilot holes for the mounting screws, make sure they're in alignment. I often skip this step and then end up with things that are a little cattywampus, usable but not quite centered, so I was a little more careful this time. Okay, that came out pretty good. And I'd like the transformer as far from the circuit board as I can without actually hitting something. That's looking pretty good there. Scooch the transformer slightly further forward, give it a little bit more clearance between the ground lug and the switch here. That's pretty good. So I need to mark that hole. And while I'm at it, I need to mark the location of my fuse. Okay, all the parts are machined, drilled, whatever. Tapped as required for the various modifications. I have a couple dead holes here, or blind holes rather, for alignment pins on switches and potentiometers. And transformer mounting hole, fuse mounting hole, and I have this little bracket ready to paint so it looks like it goes with the rest of it. I also want to touch up with some paint that milled out area so it doesn't jump out as the only shiny part on a black anodized surface. The Telema toroid transformer comes already with the foam pad on the bottom and a structural insert in the middle, so you don't need a steel plate or any of those things that sometimes you need to mount toroid transformers. Alright, that came out pretty good. Got the ground lug on there and the bonding switch. Transformer looks good, fuse holder looks good, their associated screws are fine. Power switch is on there with its anti-rotation ring into its blind hole. So I'm probably going to put off assembling the rest of this till tomorrow, but doesn't look like there's anything else mechanical to do on this. I've decided that I don't want to rely on the solder mask to avoid a ground connection between the circuit board and the case. So I've marked where I need to cut away the, well, if not cut away, at least sever the foils on the top and bottom of the board from along the edge to the main ground plane. And so I use my Dremel cutoff wheel, not the most precise job I've ever done, to cut through just deep enough to remove the foil. So there shouldn't be any place where the ground plane can make it through now to where the circuit board fits into the slot in the case. And I've left the integrity of this one, even though I cut into it accidentally. The foil going to it is still intact. At least half of the width of it is. So that should be okay. If I do decide to do something different with this, I can still use this mounting hole here as a ground point. First order of business on the circuit board is to solder on the IC sockets. Now these do not come with the kit, but Except for production work, I feel that anything like this should have sockets. And I should note, I may have missed this before, that the one Zener diode in the kit, which looks very much like the 1N4148 diodes, apparently the kit manufacturer was getting feedback that people were putting the wrong diodes in, not being able to tell the difference between the Zener and the other diodes, so they actually stick the Zener, although it's unsoldered, into the circuit board in the correct position. Just for yucks, I'm checking the Zener on my Atlas, Peak Atlas Zener tester. It's coming in at about 5.9, and if I change the Zener current, it stays around 5.9. Goes up a little bit with current. It's called out as a 5.6 on the schematic, but it's not that critical. Up next are all the diodes. There's the Zener diode there in the middle of the screen, and then the two 1N4148 diodes and the single 1N4004 diode. And then also the full wave diode bridge. And then all the resistors are soldered to the board, except for the potentiometer. And then the 4 transistors. And then the LED is soldered on. It has a bend in it, and it's adjusted to fit into the hole in the case and go all the way in as far as it'll go, which still doesn't bring the front of the LED to the front of the case, by the way. There was actually enough lead length there where I could have countersunk that hole a little bit to allow the LED to go in further, but I think it'll be fine that way. So the 3 small electrolytics, the 4 large electrolytics for the power supply, and the 2 smaller yellow caps there. I'm not sure what type they are. They don't say in the non-existent bill of material, so they might be polyester or one of the other types like that. And the 2 terminal blocks for incoming signal and for transformer secondary are on there. Since my transformer voltage might be a bit higher under the small load of this amplifier than I had anticipated, that means the voltage regulators are going to be dropping a bit more voltage. I don't know how hot they're going to get. Too lazy to do the calculations. Plus, I don't know the current consumption of this amplifier. I doubt it's more than a couple hundred milliamps, if that. So, to try to hedge my bets, I'm going to fabricate a couple of aluminum heat sinks for these guys and do that before I finish the assembly of this. After penciling out my heatsink design, trying to get up and away from the voltage regulators a bit but not hit the top of the case, and then fan out to cover all the space that can be covered without obstructing something else. And then I've transferred it into a cut pattern on a sheet of 1/16 inch thick hardware store aluminum, using my sheet metal shears to chop this down a bit. Alright, and now over to the bandsaw. Okay, heat sinks are cut out and holes are marked for the 540 bolts that'll hold the heat sinks to the voltage regulators. And that's, by the way, the common size that these are best with. A 632 is a little bit too big. 540 is a little bit too small. A 540 is a common size that fits them very well. And I thought about just tapping these, but I think I'm going to use the nuts on them. And by the way, it's always best, or usually best, to use the 540 nuts on the front side of the regulator, and they're sized just about perfectly with their hole centered, and the flat, it rests up against the body of the regulator and prevents it from rotating. If you use a 632, it's not going to fit, and that's another reason to use the 540s. Notice that the two heat sinks, although they're pretty much the same area, this one has to be cut out with a bit more space between the vertical tab and the folded over part so that it doesn't hit some components that are right next to the regulator. This one has a bit more of a generous tab width to it. I can use my bending brake to bend that. I have one of the teeth taken out so that I can not bend the main part. Well, that didn't work out so well. It was trying to bend the flat part anyway. There wasn't anything to support it there. So I just reverted to my old way of doing it, putting it in a vise, grabbing it with a wide pliers and bending it around. The downside is now I have to go and clean up this surface so where it mates the back of the regulator, it has the smoothest surface possible. Now I have to do the other one. So I think those came out okay. Now it's never optimal to make heat sinks this way. It's best to have the radiating area as close to the base as possible. You know, ideally there should be fins coming to either side, and there should be lots of surface area right here, because the thermal conductivity, you know, around this bend and over here to here is far from ideal. It's not going to work nearly as well as a heat sink with more thermal mass close to the regulator. But in this case, with this design, I don't see how I can really do it much better. If it turns out that I still have a regulator overheating condition, I still have the option of remote locating them, quite possibly just right to the top of the case, bolting them to the top of the case through some thermal pads, thermal insulation pads. That doesn't make any sense, does it? They're electrical insulators, but they're thermal conductors, to the top of the case, and let the case be the heat sink, and then just run some short wires down from there to the circuit board. That is still a possibility, but I'd prefer not to have to do it that way. We'll definitely try it this way first. Okay, this is the test fit. I just want to make sure that they're not going to hit each other. It looks like they've got about the gap I expected. And I don't think they're going to hit the top of the case. I don't have the regulators nearly as far down as they could go on the board right now because their leads are hitting the case, going through the circuit board, then hitting the bottom of the case. So I can go upstairs and test fit the top, make sure these aren't too high, and then I can go about mounting the regulators in here. I have to put some thermal paste on these as well if I can find where I stored it. Yeah, that's looking good. That's plenty of clearance. It still has some room for air to move around the top of the plates. And it keeps the mounting screws up above the capacitors, so if I want to take this apart in the future and change the heat sinks, the screws won't be obscured or blocked by the other components. So I think that's the ticket. There are the two regulators soldered to the board. I have them up just slightly higher than they would normally be, based upon the change in their lead size. They normally wouldn't sit down more than just a hair lower than this anyway, so I could have just let them sit all the way down like that. It would have been fine. Now to apply the heatsink grease and bolt them up. Okay, there's the two heat sinks. I didn't get the 90-degree angles precise, but they're on there. The relay is soldered in. The two headphone jacks are soldered on. Interestingly enough, there's a little couple of plastic bumps on the part of the green case that contacts the circuit board there, and they're not at the same height as the wide spot on the set of 4 pins. So if you just put it down where everything meets, the jack will actually tilt up towards the front. So I took those off with a razor blade, or an X-Acto knife rather, to make it sit more flat. Just doing a sanity check fit up with the front of the case in place and making sure the pot lines up and that there's no weird height issue with it sitting on the board, and it looks like it's pretty much the way it's designed. The phenolic back is sitting up just a hair, and I wish I had a good way of fixing that. Maybe I could put a piece of tape on it to hold it at exactly the right height. That might be the ticket. I've soldered a wire right onto one of the peripheral holes in the designated grounding mounting hole, and that can run back to my bonding switch. Probably would be better to have a larger gauge wire, but I don't usually stock a lot of large gauge wire in my lab, so this will have to do, I hope. Okay, volume pot fully soldered and ICs installed. Interestingly enough, these ICs don't have the usual dent over pin 1, they just have the dot at pin 1. That's an unusual case molding decision on their part. Before getting to the point of wiring up the case, and especially the transformer, I want to make sure that I have the colors correct and the windings correct. Here is the Telema datasheet mechanical drawing. Shows the 4 primary leads, yellow, red, black, and violet. That's these, and they're smaller gauge wires, as of course they would be on a primary. And then the secondary would be blue, red, brown, and green. And here those are a bit larger gauge wire for the higher current. And here's the schematic. I hate it when schematics are done like that. At least hint that it's a coil, guys. I don't know if that's a Euro thing or what, but in my mind it doesn't qualify as a schematic. Anyway, there are 2 primary windings, and they're marked 0 volts and 115 volts, which is also squirrely. I presume they mean neutral by the 0 volts. Since I'm running it off of 115, these 2 coils should be in parallel, so it probably should be yellow and red together and black and violet together to the 115 volt line. And then the secondary is 2 windings of 12 volts each, and since I'm looking for the equivalent of a center tap, I think I should be able to tie the red and brown together for the center tap. So we're going to try that out now. Okay, my transformer is wired up like that to the line cord. I have neutral going to the yellow and the red, and the hot going to the black and the violet. On the secondary I have the red and brown twisted together, and they're just currently hanging out in space. And then the green and the blue which should have roughly 24 volts between them, are wired out to my multimeter in AC volts mode. So power's on, and I'm reading a totally unloaded 32 volts, which shouldn't surprise anybody. And if I go from one side to center tap, I've got roughly 16 volts, and on the other side of the center tap also 16 volts. And just for yucks, I put it on my Simpson 260, and on the 50 volt range, which would be here, it's reading, let's see, that's 35, so it's reading 32 volts also. Of course, that's without any load. Since I'm going with the circuit configuration of having no connection between the case and the circuit ground, unless I select it with this switch, I need to make sure that my RCA connectors are isolated from ground where they go through these holes. Now, I did measure these, and I don't know if it's an industry standard or not, but I selected these Nutric Rean, that's R-E-A-N, that's a brand of Nutric, and it's their NYS 367 series of RCA connectors. And then you add a suffix to it to determine the color, and they have quite a few colors. I've got a black one and a red one, and they come with these insulating washers, and one of the washers has this raised lip on it, which is exactly the right size to fit and center into these holes, thereby providing a centering effect and insulating effect, so the metal housings can't touch the case where they pass through. So these would seem to be the ideal RCA connectors to fit this particular case. So you can see there how that has a centering effect that keeps the metal parts isolated. There is the jack mounted, and it's solder lug put on there, and one nut tightened up. It does come with two nuts, and I'm going to put the other one on there because I don't know what else to do with it. So it's like that. I'm making up the snubber, which are a couple of loose parts that do not go on the circuit board, but they were included with the kit. It's a 1 nanofarad capacitor rated at 1 kilovolt and a 100 ohm resistor at 1 watt. And these get wired in series with each other and then wired in parallel with the power switch. And I'm going to parallel the contacts on the switch because it is switching an inductive load, and paralleling the contacts will increase the current rating, so its ability to withstand arcing and so on should be slightly better. But first I have to form up this and get some insulation on it. Okay, I've got my snubber wired across the switch, the power switch that is. One side of the transformer going to there, and the other side is the fused hot, and the hot comes from the hot terminal of the IEC plug. The neutral goes directly to the transformer primary. I've got the ground of the IEC plug going to the rear chassis, and from there to the bonding switch. I have pigtail wires for common left and right, ready to go to the circuit board. I need to wire up my bonding wire from the circuit board to the bottom of the switch there. And now I've got that bonding wire on the switch. So if I raise the switch, it'll connect the circuit ground to the earth ground. And I don't expect to use it, but it's there in case I want to for some reason. Okay, oh, I need to get a fuse for this thing. I have to figure out an appropriate value and see what's in my junk box that's at least reasonably close to that. Yeah, the smallest I had in my junk box was a 1/10 of an amp. It's a 250 volt 3AG style fuse. I estimate that this probably only needs to be like 0.02 amps, but so this fuse is considerably oversized. Still, it's a pretty small value fuse, and if something shorts out in here, it's going to blow. What it won't do is go on an overload of the circuit, but being just a little op-amp circuit like this, I don't really expect it to ever do that anyhow. Should deal with catastrophic problems anyway. Alright, the secondary of the transformer is wired up. The virtual center tap is on the center, and then the outsides of the windings are here. Now for the analog inputs. The main headphone jack also has a insulating centering ring, so it's designed to be isolated from the chassis. So I need to realize that the plastic part sticks out a little bit too far here in the front, and that's what this fiber washer is that comes with it. Goes on like that, and that brings it a little bit more flush. Now there's this other ring, supposed to be a decorative ring on the front. It also has a centering insulating bit to it, which the only way I can put it in is facing the other one. So that goes on like that. I should point out I didn't show it, but the center part, that's the silver colored nut there, actually has threads on it, and it threads, or it passes through the two black insulators and then threads into the inside part of the jack. So that provides the ground connection for the jack, but it is not connected to the chassis. And there's my clearance hole for the 1/8 inch jack. The potentiometer's fitting through there. I can see its anti-rotation key sticking through the hole. Now of course it's not going to rotate because it's on the circuit board, but I'd rather have the clearance hole for it and not have to cut it off. And it needs to do something or it's not going to fit in there properly. And then the washer and the nut are put on the volume control shaft. Now I knew that there was going to be a fairly tight clearance between the fuse holder and the jacks on the back and the back of the circuit board. It's plenty far away that there's not going to be any arc jumping or anything, but just in case one of these input wires should, fall out of the, somehow come loose and fall out of the terminal block here, I don't want it flexing over and hitting that AC hot. So I'm going to rig up some sort of an insulator for that. I probably could have put some shrink tube around that, but it's kind of late for that now. I'm going to do something else instead. One obvious thing was just to grab them with the pliers and bend those fuse tabs up a little bit, make a bit more clearance. I put in these two bolts here to secure the front panel to the bottom of the chassis, and that requires a number 42 hex wrench or hex driver, number 42, and that's a metric size, of course. And then two Phillips drive black anodized screws to hold the bottom in, And I have to organize these wires a little bit. Yeah, that's a bit more like it. Boy, this is heavy with that transformer in there. Plugging in my IEC style power plug. There we go. So I just want to do a power supply test at this point, see if there's any magic smoke. Got a green LED. I heard the relay click. So I need to go here and probe some voltages on the ICs. Can't easily do that with the camera, but I'll let the narration go on. So let's see, there's circuit ground, and this should be minus 12 volts, minus 12 volts, positive 12 volts. Okay, power supply is basically working. So I think I'll plug it in and see what happens. Okay, I've got a set of RCA cables coming from my patch bay, and that should be the CD player's output. So I gotta queue up a CD. Got my full-size Sennheiser HD650 here, which the camera doesn't want to show. I'm going to use these for testing. So they're plugged in there now. It's got a nice feel on the jack. It plugs in with nice authority. Got the volume turned all the way down. I'm going to listen. As I turn the power on, there should be no pop. There's absolutely no sound in the headphones. No hum, no nothing. I did hear the relay click, which means that the headphone jacks are connected to the amp. So I'll just get my remote here and play this CD. It's playing, but of course I'm hearing nothing because the volume's turned down. Turned up just a little bit and I'm hearing stuff. That was one of my favorite CDs, the original Switched On Bach. I just happened to have it laying out here because I'd been listening to it recently. So let's do a warmth check. These don't feel warm at all. Even with the volume turned up, I don't know, a quarter of the way, I was getting about as much volume as I cared to get from a set of headphones. So that means that this should handle less efficient headphones and still have plenty of volume. I mean, there probably are some types of headphones that this still isn't powerful enough to drive, but certainly for these dynamic headphones I've got here, full-size ones, it's got plenty of oomph. I'm going to do a little bit more listening. I've just turned the bonding switch on, so the circuit is connected to ground. I don't hear any hum. That suggests to me that my CD player does not have its circuit ground connected to earth at its end, so there's no ground loop or anything. But that's not always the case, but I don't see any need to leave it on, so I'm turn the bonding switch back off. It's sounding really good on the headphones. No complaints about the sound quality. Plenty of volume. And because it's DC coupled, it's got absolutely no frequency roll off. It's going to reproduce anything that's coming into the input jacks. Let me check these out here. I don't detect any warmth on these at all. Everything's feeling really cool in there, so I don't think there's any problem with this transformer running in here. If those were going to get hot, it's already been on for about 5 minutes, or probably pushing 10 at this point. It's not been all on camera. And there should be at least some radiated heat out here if those are getting warm, and I don't think they are. The included knob just pushes onto the shaft. Probably takes 2 hands. Okay, so one more look around inside of this. I am a little disappointed that the aluminum finish knob, I think it actually is aluminum, although it's very thin aluminum, and it's mostly a plastic core that pushes onto the knurled shaft of the pot. It came in kind of scuffed up. It was just stuck in the parts bag with everything else. And I also said something wrong before. The pot needed to be roughly at the 12 o'clock position to get nice and loud with that line level input. It wasn't at the 9 o'clock position as I originally said it was. It needed to be. Of course, I was getting used to it and I was turning the volume up a little bit, so there's that. Anyway, so circuit board is not mounted to anything, but it is sitting in the slots of the case. It could slide around. It's being held in by the nut on the shaft of the potentiometer and the nut on the front of the 1/4-inch headphone jack. That's what's keeping it in place. The wiring is kept short and simple. There's no need to shield something like this. And the toroid keeps its magnetic field nice and tight, so you don't have much radiation from that. But even if you did, you wouldn't expect any real problem with a circuit like this. If this was a much more sensitive amplifier or something, maybe, but not in this instance. The tolerances I picked for the distance between the... I don't really like that too much. I should bend that around. Yeah, I had the hot wire from the IEC connector going to the fuse jammed in between the transformer and the bonding switch, which isn't the best place for it to be. But yeah, so the input circuit is totally isolated from the case, unless of course I throw the bonding switch. The circuit itself is isolated from the case. I do have the wire from the circuit ground through the bonding switch to chassis ground if I choose to use it. The heat sinks have plenty of clearance. This probably could be somewhere else. It's not hurting anything being under the heat sink, but I might be able to route it a little differently. Actually, it's probably pretty good under there, come to think of it. It's not causing any problems. I'll just tuck it down a little further from the heat sink, though. There, like that. That's better. IEC connector has adequate clearance, but it's tight as I intended it to be. Let's see. Positive regulator heatsink hangs over the transformer. Negative regulator heatsink hangs over the 1/4-inch headphone jack and part of the relay. I've got my little snubber sitting on the power switch there, and that seems to all be working pretty well. I'll make sure my heat sinks are nice and tight before I button up the case. Now the case is set up in its extrusion to have a ridge on one side and a groove on the other side, and then the bottom is exactly the same, so you have to flip the top of the case so a ridge goes into a groove or it won't close properly. Yeah, it fits together nicely on both sides. I just need to put the remaining screws in. And these screws, by the way, the case is not pre-tapped for the screws, so they go in a little bit hard, and the screws aren't a self-tapping type, so I suppose if you wanted to and you had a tap of the appropriate, I'm sure it's a metric size, you could tap the slots in the extrusion to make it a little easier for them to go in, but they seem to work okay, just jamming them in like I did on the bottom ones. By the way, the case kit does come with 2 spare screws for the front and for the back. The screws I put in on the bottom to hold the fuse holder and the transformer are approximately the same height sticking up as the front panel, which is oversized relative to the case. It does hang out all the way around, whereas the back panel is pretty much exactly the same size as the case. I kind of wish that they'd made them both the same so that it could rest on these two, but as it is, I'm going to put some feet on them. I do happen to have handy here a set of self-adhesive felt pads, which should make decent feet for this. I'm also going to look around and see if I have some better ones. Found some clear rubber dome feet that are slightly taller than the felt ones. I think those are more appropriate, and I have 4 of them. How handy. And there are the feet. So there is the finished product. I think I might make a label for this, if only to remember where I filed the manual for it, which I'm going to discuss next. I just used my Brother P-Touch label maker with the TZ tape. Luckily I had a 1/2 inch wide white on black tape roll in stock. Should be about right. HA-PRO2 headphone amplifier in up position, switch bonds, circuit common to chassis/earth ground. And there's that. Makes it a little bit more professional. And it reminds me what that switch does. The one on the front is obvious. I don't need to put any labels on this. Success! Okay, for the documentation. The HA-PRO2 comes with 0 documentation. You just get a bag of parts and you're left to figure it out yourself. It doesn't mention at all the necessary type of front-end circuitry. You just have to know about that. So what I've done, I looked online and looked for somebody who had already produced documentation, and there wasn't anybody. So I traced out the circuit board and scaled it accurately, made my own circuit board layout. I did find a circuit board layout, by the way, online, but it was for a different version of the board. Had some minor differences. The most notable being that the 1/8 inch headphone jack, or the 3.5mm headphone jack, was not present on that version. And there were some inadequacies, I should say, in some of the descriptions on the board. So I have conformed this one to the HA-PRO2 revision 4 of the board, which is the one I have described here. As it says here, HA-PRO2 version 4 printed circuit board, stereo headphone amplifier circuit board layout. And I made this, even though I copyrighted it, it's available for anybody to use, and as long as if they reproduce it in some way, that they don't remove my name and copyright from it. And if they put it on a website or something, then they should credit me as the author. But otherwise it's free use, that's my intention. So in addition to just fixing some problems with the parts layout, I put some additional information in there. Right, so I clarified that you would need a power transformer, which is not on the circuit board, and it's not part of the kit. It should be a 24 volt center tap, and I have no idea what the current draw is. I said here it should probably be at least 300 milliamps. It's kind of hard to actually find a 24 volt transformer that isn't at least 300 milliamps, so you know, you could find some small ones, but the more common ones are at least this big. And the transformer I used here is about twice this value. Anyway, so I identified that this mounting hole is the only one that's used for grounding. Identified that it is connected to circuit ground, so if you put a screw through this into a chassis, then the chassis will also be at circuit ground. I point that out here. I suggested the transformer brand and model number I used, 62052. The 62053 is a bit higher voltage, so not ideal, but it could be used. 62052 is definitely the one I used, and it's closest to the correct desirable value. As for the RCA jacks, if you're just building the circuit board, you can use whatever you want, but if you buy the case kit, as I did, then you're going to want jacks that fit the case, the holes drilled in the case, without a lot of mucking around and guessing. So I found these nice Nutric Rian or Rion or whatever it is brand RCA jacks, as I mentioned before, the NYS 367 series, and then you just add a suffix on there. -0 I think is black, and you know, -2 or whatever is red, and so on. Those are perfect for this case, and they're a high quality connector, and I can't think of anything better than that to use with these. Identified which channel is right, and that's following the convention on the jacks, for the headphone jacks, of the tip ring sleeve. I didn't actually know this. I always assumed that the tip was right, but it turns out from some online research that more commonly the ring part of the headphone plug is right, and then the tip is left. But there may be some variances in that. And the nice thing about this is you can't change the wiring of the jack, but if you find out that the headphones you're using are wired the other way around and you want to keep right, and left, all you have to do is swap the wires coming from the jacks and swap left and right here, and then it'll swap them up front. The other thing I did in this documentation was I gave all the parts part numbers. There are no identification numbers on the circuit board, which makes it hard to make a schematic for it, because you can't tell which parts on the layout go with which parts on the schematic. So I've added, you know, C1, C2, 3 and 4, D1, you know, and it's so on and so on. Power connectors TB1, input connectors TB2. If you had an older version of the board, there's another terminal block that goes here. It's just the same as this one. And if I had done a drawing for that, it would probably be TB3. I identify the relay and its connection diagram. I identify what the LED is for. I identify emitter-based collector pinouts on the 4 transistors. I make sure that plus is identified on the capacitors, that's the electrolytic ones. And also I list the capacitance and the voltage rating. On these smaller capacitors, I mentioned that they are 100 nanofarads, 100 volts. And let's see. All component values are shown. On the op amps, I identify circuit 1 output, circuit 1 minus, circuit 1 plus, those are the inputs. V minus power supply, V plus power supply, circuit 2 output, circuit 2 minus input, circuit 2 plus input, and the same for the other ones. So that gives you the pinout right here. According to some information I found online, some versions of this kit may ship with a 50K pot or a 10K pot. So I showed that either one might go here. But on my particular kit, the pot was a 50K pot. Although I've certainly built volume controls before that used 10K pots and it was fine. And by the way, it is an audio taper potentiometer, which any potentiometer used for volume control should be audio taper, or you end up with all the volume control over at one end of the pot and then the rest of it doesn't seem to do anything. Let's see what else. I identified the basic outer dimensions of the circuit board, 4 1/4, 2 3/8. The fact that these are in English units suggests to me that the original design might have been from somewhere in the States. Otherwise I would have assumed that they would have used metric dimensions, some nice metric dimension. As many of these kits come out, they're actually rip-offs of some commercially available item. I don't know which item might have been ripped off to make this, if that's in fact what happened, but that might support why it has these dimensions. Now, for all I know, the 4 1/4 dimension might just be because this is a standard extruded case design, no matter who makes it, and those are set up for English units, so that might also factor into it. The other thing I added on here was I showed center lines for the LED 2 headphone jacks and potentiometer. This is drawn exactly 2 times scale. So if you were to take the schematic and print it out at 50% scaling using your computer's or your printer driver's scaling feature, or if you can't do that, you could put this on a photocopier and tell it to reduce to 50%, and you'd end up with a diagram that's exactly the same size as the real board, and you could use that as a template for drilling your mounting holes if you're doing it that way, and if you're making a front panel and not using the case kit, it gives you at least the horizontal centers, if not the vertical ones. I also note here that going by the tip is left and the ring is right. Going by that, this 1/8 inch or 3.5 millimeter jack has the left and right reversed from what it is on the 1/4 inch jack. Now somebody may say, oh yeah, don't you know that the headphone jacks using the 1/8 inch one are indeed reversed as a standard, and if that's the case, I didn't find anything online to support it, nor did I dig around because I don't own any headphones that, at least not ones that are here at home, that have the 1/8 inch jack on them, so it wasn't convenient to test it. Okay, the other part of my documentation, and I think I forgot to say that I am sharing these, and the way I've decided to share them is I put them on my own file share webpage, which I'm going to put a blurb in the description probably of the YouTube video, and also, if I remember, I'll put a caption in the video itself showing what the URL of that is, so anybody building one of these things can at least have some decent documentation. I figured out the schematic as I said before. I show in dash line boxes those parts which are not part of the circuit board, and if it's not part of the kit either, I also mention that in text. So starting with the power, I mentioned that the RC snubber is drawn below exactly as it's shown on the silk screen of the circuit board. There actually is a little circuit diagram there. So that's what's here, the 100 ohm resistor and 1 nanofarad capacitor in series wired across the power switch. And normally I would put the power switch on the hot side, which I did here. For the sake of drawing this and making it fit, since the drawing was getting a little crowded, I showed the fuse on the negative side, but the way I actually built mine was coming in on the hot connector, going through the fuse, then going through the power switch, then the transformer and back to neutral. But it works either way. Once again, I show which transformer I'm recommending to go with this. Duplicated the information from the parts layout. TB1, terminals 1, 2, and 3. And I mentioned the bonding switch, which I don't show here. That's just my own little thing I decided to do with my kit after making these drawings. So I said to avoid ground loops, the case may be earthed, but the circuit ground might be isolated from earth. This depends on the selected case and the circuit board mounting method. I didn't say here, but it also depends on whether or not the circuit common is earthed at the other end of the cable that you're plugging into the RCA jack inputs. It's okay in most cases to have the circuit earthed at one end, but you don't want it to be earthed in two places. So there's differences in how various stereo equipment and so on handles that, and that's why you want to be careful with that so you don't get hum from a ground loop. The secondary, I'm showing a center tapped secondary. On mine it actually had the dual coil secondary, but as I mentioned before, you can wire that up to be just the same as a center tap secondary. 24 nominal, which is barely enough voltage to assure that the voltage regulators work properly. So I'm kind of happy that my toroid is beefier, so its voltage won't sag so much under load, and therefore it's going to be a bit higher than 24 volts, which assures that the the voltage regulators don't get starved for adequate voltage. The AC from the transformer is rectified with a full wave bridge. Capacitors do initial filtering. Then you've got your 7812 positive 12 volt regulator and your 7912 negative 12 volt regulator. And then two more capacitors. They're the same values as the input filter capacitors. This is really unusual. I went back and hit my data sheets again, and they recommend that for virtually every situation you only need a little dinky capacitor for these, and most times you don't need it at all, but it's good assurance or insurance to put them on just as a matter of course. And something that I didn't do here, and the circuit designer should have done, was if you ever let one of these linear voltage regulators have a higher output voltage than the input voltage, current will flow backwards and it will destroy the pass element of the regulator. And it has no internal protection for that. So if you have a circuit using these and there's just no way that you would ever have a higher voltage on the output than on the input, you don't need the protection diode. This circuit having such a large capacitance on the output, it really would have been a good idea to have the protection diodes in here. If you accidentally crowbar these things, just futzing around with the board and accidentally short them out, you lay the circuit board down on something that's conductive and it shorts these out but not these. 470 mics can store enough charge to push enough current back through here to destroy these voltage regulators. But the designer of this circuit did not put provisions for protection diodes on here, so I didn't use them either. But if you're curious, on here you would take a diode coming from here and going back to this point, facing in that direction, so the cathode's over on this side. And with the negative regulator, you'd have a diode going from here to here, facing this way, so the cathode's on this side. If you want to jury rig one up on yours, you could do that. And finally, there are these two smaller capacitors. They're 100 nanofarads, which are on the board closer to the op amps. Ideally, each op amp here should have its own decoupling capacitors like this, but the circuit designer just decided to use one on the positive, one on the negative supply rail, and put them pretty close to the op amps. And since the op amps are all physically very close to each other, it's obviously adequate. It's not maybe recommended practice, but it's good enough. So now, having established how the plus 12 volt regulated supply rail is generated for the op amps and the negative minus 12 volt regulated supply for the op amps, and it goes nowhere else, by the way, it's only used for the op amps, that's why there's no lines coming off of this, it's just for the op amp power supplies. So now here's the front end of the circuit. I say that parts in the dashed outline are not part of the kit. Here's your two RCA jacks, and their wiring goes to TB2, terminals 1, 2, and 3. Identify right and left here, and identify that they are line level inputs, and it's expecting a stereo signal. And once again, I duplicate the information from the other drawing and show my suggested parts that you'd want to buy. And that's, again, if you're using the case kit. But even if you're not, they're a good choice of jack for probably almost anything. Here's your dual potentiometer. I showed the 50K parts that came with my kit, not the 10K. I mentioned again it's the volume control, that it should be audio taper, and this is the rear part of the pot, and this is the front part of the pot. So I'll just focus on the right channel circuit. This is a super simple circuit. To go from line level to headphone level requires a gain of roughly 4, and that's exactly what this amplifier stage has here. The 10K ratio with a 2.2K resistor gives you the approximate gain of 4. And it's configured as an inverting amplifier. There is no subsequent inversions to uninvert it. And in spite of what some people might tell you, this makes absolutely no difference. The human ear cannot tell whether the waveform is inverted or not. And the more you think about it, it makes perfect sense why it doesn't. Because if you're thinking about a pulse of sound coming out to you, which you would want to be correctly in phase, that's not what the plus and minus signal on the audio waveform means. The pulse of sound coming out to you from the speakers is an amplitude modulation, not a plus and minus signal modulation. So people get confused over that. So inverting here is fine. And then to get enough current, it uses the other 3 op amps. And by the way, these 4 op amps are all in 2 ICs, and I've identified them here. IC5 Part A, IC5 Part B. And if I'd really been thinking when I made this drawing here, I would have used A and B instead of Circuit 1 and Circuit 2, but I didn't think of it, and now it's too late. And then here's IC6 Part A and Part B. So it's using 3 non-inverting buffers in parallel to get enough drive current for the headphones. And because you don't want to directly couple multiple amplifiers together, they're isolated through low value resistors, 2.2 ohms each. That allows them to be slightly different from one another and not damage each other. You can have a very tiny voltage difference between these, and that'll be dropped across these resistors, but otherwise they're so low value that they don't have any other effect in the circuit. And then the left channel is just the same. You end up with these 2 amplified signals coming here, and they go through the normally open contacts of the relay. Here and here. And then they go out to the headphone jacks. And I'm showing both the 1/4 inch and the 1/8 inch or 3.5 millimeter jacks. And I mentioned that the left and right are swapped between the 2. I actually didn't draw this correctly. It's a mistake I made. These are actually the normally closed contacts here. But at least it's represented correctly here. So what's that relay doing there? Why is it in between the amplifier and the jack? Well, the reason is that when you first turn an amplifier like this on, you don't want it to pop, and you don't want to hear the weird little noises that the op-amp amplifiers make when they're powering up. So if you happen to have the headphones on and plugged in when you turn the power on, you don't really want to hear all the power-up noises. So that's what the relay does. It doesn't close until the power-up is complete, and then it connects the amplifier to the jacks. You also will notice that there's no AC coupling here. It's direct DC coupling throughout. No capacitors. And again, these are relay contacts, not capacitors. This is great to give you the most uncolored, direct, unblemished signal path, but it has the downside of if you have any DC component to your input signal, that DC component will also be amplified by a factor of 4, and that could be a fairly substantial DC component presented to the headphones, which is not great. And I'll talk about how that is solved here in a minute. So now this remaining circuit, this needs its own power supply because it's driving a relay and some other stuff. You don't really want to have it hanging off of the voltage regulator circuit, even though it really needs 12 volts. So you really could do it that way, but it's best to have its own power supply. So one side of the transformer is, transformer secondary that is tapped off, and instead of going through the diode bridge here, it goes through its own half-wave rectifier using the 1N4004 diode. And then a 47 microfarad 50 volt capacitor for a bit of filtering. It doesn't need a lot of filtering for this. If it has some ripple on it, it doesn't affect anything in this part of the circuit. It just doesn't need to be that clean. First thing we do with that approximate 12 volt unregulated power supply is we run it through a current limiting resistor, and then through the power on LED on the front panel. So that's how we get the power on. And then we have this nifty little circuit here. Here's the coil of the relay I talked about earlier, and it has a back EMF snubbing diode across it, so when the relay is de-energized, it doesn't generate a high voltage pulse, which would cause noise and isn't really that great for the rest of the circuit around it either. The coil of the relay gets 12 volt applied to one side, and on the relay it's called the plus side, but I checked it and it does not have an internal snubbing diode, which is why there's one outside of the relay to do the job. Some relays have built-in snubbing diodes, in which case they usually have a plus on them. The relay has a plus, the circuit board has a plus, but it doesn't have a diode in it. At least the relay in the kit supplied to me did not have the diode. And let's see, so then you need to energize the relay, and the way you do that is provide a current path to circuit ground, and it's done through this Darlington pair of identical NPN transistors. I don't know exactly what the specs on the C1815 transistors, and all four are the same part number, by the way. But when I put them in my transistor checker and compared them to a 2N22, which is one of the most common general purpose NPN transistors, they were very close. So I would just say these are general purpose NPN transistors. Anyway, so when you turn these transistors on, it provides a current path to circuit ground for the 12 volt power supply, and that energizes the relay coil, which activates the contacts, and then they close, and then the amplifier is connected to the headphone jacks when that happens. So we want to delay that so the op-amp part of the circuit has a chance to power up and stabilize before we energize the relay, and that's what this circuit here does. There's this fairly high value resistor coming from the 12 volt supply, charges this 10 microfarad capacitor. Ignore these transistors down here for the moment. When the voltage on this rises high enough to satisfy the 5.6 volt Zener's reverse voltage, then it will break down and allow current to flow through here into the base of the first Darlington transistor, which turns it on, which turns on the second one, and then it conducts the current through the relay. So that charging here takes some time when you turn the power on, roughly 1 second, before this cap charges up enough to reverse bias this Zener and turn the transistors on and turn the relay on. Now, what happens when you turn the circuit off? You also don't want to pop, you also don't want to hear the op amps going like that, like they do as their power supply slowly drops as the capacitors discharge. So as soon as you turn the power switch off, there's almost no capacity in this small capacitor here. It's only 47 mics, and therefore this diode here will dump charge from this capacitor up here, trying to satisfy the power being drawn by the power on LED and by the relay. So it basically discharges this capacitor instantly, and therefore this voltage drops instantly. The Zener is no longer reverse biased, the transistors turn off, the relay turns off, and then you have a few seconds for the capacitive charges here to diminish to the point where the op amps stop working. So that's how you get the soft on and soft off feature of this amplifier. So I promised to mention, how does this amplifier deal with possible amplification of a DC component presented at the inputs. And this could happen just because of a circuit fault where some DC voltage is applied here, or it could happen because for whatever reason the signal coming out of a computer's output card, audio output card, or the output of a piece of stereo equipment or whatever happens to have a DC component to it. Normally it wouldn't. And on a more traditional design, you'd have a AC coupling capacitor right near the beginning, probably around here in the circuit, and that would remove any DC component before it gets amplified. But this being a direct path DC coupled amplifier, you don't have those AC coupling capacitors, and you may still have some DC coming in here. So if that happens, it gets amplified and it comes down here, and those voltages from the right and left channels are sampled by these two resistors, and they're fed into this averaging capacitor, which is a fairly large value, 220 microfarads. If you have a sustained DC level coming out of the amplifier, not just a transient one, not something due to subsonics, it has to be fairly sustained, several seconds at least, then that DC component will charge up this capacitor. And it might charge positive or it might charge negative, actually, because we don't know if that DC component is positive in relation to ground or negative in relation to ground. So either way, it charges the cap up. And if it is below ground, then, to turn a bipolar transistor on, you need to have current going from the base to the emitter. The base on this one is held at ground, or 0 volts. So the only way you can get this transistor to turn on is to take the emitter lower than 0 volts by roughly 0.7 or so volts. So if this cap here charges up to something more than minus 0.7, 0.8 volts thereabouts, then this transistor will turn on. On the other hand, if this voltage is positive something 0.7, 0.8 volts, then it directly biases this transistor on, because now the base is higher than the emitter. And regardless of which transistor turns on, one of them, they're conducting through here from here to here, or from here to ground, either way. And what's that do? It does the same thing as this diode did, essentially. It's dumping the charge on this capacitor. Whatever this was, it draws it to ground right away. So this is your protection against a sustained, amplified DC voltage being presented to the headphones. It's basically a safety cutout. So really that's the overview of the entire circuit. And let's see, I explained the time delay circuit's operation here in the text. I mentioned that the bipolar supply, that's this one up here, is used only by the op amps. I mentioned again that the amplifier is intended for line level signals, not really from the headphone amp of, say, a little iPod or something, or a phone, but you could use it that way. It's just that the input will be hotter than you really want it to be, and you're going to have to turn the volume control down more to get a decent level. But you can use this as a headphone output booster from something like a smartphone or an MP3 player. Or you could just use it as it's really intended, which is to go from line levels directly out of a CD player, for example, or the output of a computer sound card. Let's see. Oh yeah, I do use the same component designations as I used on this drawing.